Hi, welcome back to my channel. This is a video on the concept of a monad in programming languages. And this has come up from basically there's been a lot of interest in functional programming languages. And one of those languages that gets mentioned a lot is Haskell. And Haskell kind of, and some people are kind of held in this kind of high regard, or in some cases, it almost seems like reverence, in terms of being like this ultimate programming language or goal. That if you master Haskell, you've really accomplished a very, very big thing, and it's a great accomplishment. And that even if you get to use it a little bit, it's really cool. And I'm not going to argue that because there are things that are cool about it. There's a lot of things to learn from it, and there's a lot of ways to expand your notion of programming languages in terms of semantics and stuff like that by studying Haskell. But when you get to a certain point, you'll see that your progress is being blocked by this big door that is locked and that has this name monad on it. And before you can move any further, you have to understand this monad thing. Now, there's lots of videos on this topic with lots of different approaches and target audiences. So what do I bring to the table here versus just trying to get into the Haskell Cool Club myself? The first thing I'm going to start with is a couple of quotes. And the first quote I found was pretty fun. I saw this on a stream by the Primogen, and he just said, "Look, monads are just a wrapper. It's like a burrito." And there's more truth to this than might seem at first. It's not just kind of a flippant remark. There's kind of some interesting depth here. Um, and so for somebody who knows a little bit more about the subject, I thought that was pretty interesting. Um, because there is some simplicity to it like this. But on the other hand, there's this. In concise terms, a monad is a monoid. The category endofunctor is of some fixed category. An endofunctor is a functor mapping a category to itself. That's from Wikipedia. And so there's this very formalized category theory definition. And that category theory definition is and does inform a lot about how monads are used in Haskell. So this also is useful. Now, between those two, and getting that presented, hopefully that just gives you enough context to go out and do your own research and try and remember that this is just two sides of the coin. It can just be a very simple thing in application, but if you need to learn more about the theory is there, and there's lots of great resources around it. And that's all you need to do is just remember it's not all just theoretical. You can just go ahead and just look how to use it practically. Of course, I'm joking. There's no reason to make a video like that. And so the question is like, what isn't getting covered by the videos that are out there already that I've seen? And what I see is that they don't ask this question of why they're there in the first place. They just take it as a given that they're there, and then their goal is, okay, we're going to explain them. This is why they're here. So I'm going to start with a question posed above. And the answer to that is fairly simple in the fact that monads are in Haskell because Haskell wants to treat everything as a function taking a single value, returning a single value, or a pure functional programming language inspired by the lambda calculus. That's it. It wants to try to be as close to those simple notions as possible. And so that's just where it comes from. That's its perspective. And we'll get into why now, what happens, what the problem monads solve later on. But this is what it's there for. What's interesting about this is that it's perfectly reasonable to go ahead and relax that expectation about being a pure functional programming language and still be a very useful functional programming language, just not a pure one. And some people ask, well, who cares if it's pure? And if you take, there's a kind of a joke that, if you get a set of Lispers and Haskellers in a room, that no one will be left standing at the end of the day because they just can't get along with each other. There will be some lively discussion about language design, that's for sure. And they just have kind of different separate approaches. But no one will ever look at Lisp and then like things to Scheme and Racket and say, oh, that's not a functional programming language. Because, that just isn't, when you look at it, just kind of, the object kind of speaks for itself. What gets interesting here is Haskell comes from the notion of being statically typed. And compared to like Lisp and Racket, which is dynamically typed. And the interesting thing about static typing in Haskell compared to the static typing that we were used to in languages like Pascal, and C and C++ and so on was void. And the problem with void is that if you want to use immutable state, right, and you want to keep this notion of pure functional programming, a function that returns void is useless. And not only that, but it actually doesn't make sense. You can't have it. You have to return a value, right? And again, this ignores side effects. And I have another video on my channel about immutability and why you actually can't not just use immutability without having to have some way of reasoning about side effects. And again, if you go back and you can say, all right, you know what, we're going to just embrace this. We're going to allow side effects only functions, do the void thing. You're fine. You're still fine. A lot of people do this and it works great. Okay. So again, you could just say, you know what, void is a return type. Awesome. If you really want to avoid this, though, and have side effects, but you still want to have the following code, and this is what's important, is that the Haskell people knew is that you needed to have code that does have side effects, because if you're not doing side effects and changing something, what's the point? You have to do I/O and things like that at some point. So you can have code like that prints out a 1 to a console prints out a 2. Well, monads allow you to do this in a purely functional way. And how they do it is really interesting, and I won't get into a lot of the details, versus to say that it did allow them to kind of go back and say, here's how we treat things, that everything is a function that takes a value and returns a value. And the thing about it is that, okay, so we go in here and we say, okay, well, what we're going to do is this is basically how Haskell works. We're going to say this is example, and it's basically its type is IO, and that unit there. It doesn't actually take in a value as a function. It turns out there's a way of relaxing that a little bit, but basically, this is where it starts getting a little bit interesting here. But and then you do the following. An example equals do print 1, print 2. And the do keyword is an interesting thing here, which is what goes off and establishes the monad and starts doing a lot of things behind the scenes, so that this is actually seen in Haskell as a function that returns a value. Well, what is that value? Well, it's a value of IO, these parentheses here, okay? IO being the monad, and the IO being a monad is also can be a parameterized type in Haskell. So it's an IO of, well, what's this thing here? And if you go to the Haskell's tutorial, it goes off and says, well, this is a representation of the unit type, much like void in other languages. And now you'll be like, okay, wait a minute, hold on a second. You just said that we're doing this to avoid the program stuff like that. You tell me about all this kind of stuff. And then now you've gone away and says, like, now you've back-ended here and said, okay, well, isn't this just adding void back to the language? And the interesting thing about it is that it's not really, because the thing about it is that you can have an IO of string, and you can have an IO monad that does return a result. And you would want that, for example, if you're reading from the console and you want to return back a value. So you need to have that. And it can treat all these IO monads as being equivalent in terms of being a parameterized type. So it can actually look at this and say, oh, the universe of IO is actually under this single type. When you're doing this with void and just having functions that don't return certain values, that becomes a little bit more difficult. But then again, people will be like, so what? If some functions will return void, so others won't. And some people even argue that basically it's like, that actually says something about the function. If it doesn't return anything, it is obviously something that's just done for side effect reasons. And again, that's absolutely correct. If you relax the programming language, don't worry about purity, that's fine. But there's subtle little advantages in terms of type checking that we can get into that makes it so that this isn't quite the same as void. But if someone came back to you and said, it's like, well, this is ridiculous. You just seem to be kind of constantly ending these concepts in a slightly different way. That's a very valid criticism. And what it comes down to is that I can go more into depth about how monads do everything, but really what it is that Haskell's just super opinionated. It wants to be this pure functional programming language, and monads are the way that they want to make it so that you can do these type of IO-like set of operations and do it and treat it as if it was purely a functional programming way. They're sufficient. They get the job done. They're not necessary by any stretch of the imagination. They have that had certain advantages, but a lot of them just it's not immediately clear why you would want to do this. And the reason is that the why comes down into why Haskell wants to be a pure functional programming language, what that allows you to do in terms of type checking and program verification. And that's a really advanced topic for most people. And here's the thing. What this does is Haskell as a programming language takes the simplest code that we usually present to people. You run Python, you type in two print statements, and it goes, oh, look, you prints one, and then it prints two. Wow, okay. You understand that kind of code. Do this, do that. Simplest code as possible. It takes that and says, oh no, you have to turn this into a context in which that operates within the context of a monad of some kind, and you have to determine what kind of monad works best, and you have to make sure that you use the right monads and the types and all that to do the static type checking, and all this to keep this purely functional as possible in terms of the language. So you've now taken the simplest bits of a program for a lot of people, in fact, most people, and turn them into what can be the most complicated part of the type system. And that's a massive leap. It's huge. I can't really, I can't stress enough that if you're struggling with it, there is a really big reason for it, because basically it's turning around what you thought was really simple, and almost every other case is really simple, and puts it inside this theoretical framework that is just bogglingly weird when it comes down to it. And the reason being is that, oh, well, there has to be something that's fundamentally better about this. And from a practical standpoint, no, it's not. And this is where a lot of people will kind of not do this because they're either Haskell fans or they're trying to just not be opinionated on certain types of things and just present. Well, this is how monads work, and it's great for presenting that information. The problem is that this lives in the larger context of programming, and people write programs to do certain types of things. And outside of a few domains, this complexity is just not worth it. It just isn't. You can do a lot of things around it to make it so you could do a lot of functional programming things and do things a different way and still get a lot of these benefits. And there's two things that have happened in it. Just practically this pure functional programming thing, it's great when you need to do things like program validation and do advanced semantics type of stuff. But for the vast majority of domains, outside of certain types of things like security, they use some stuff there. There's some stuff in basically verifying IO kernels. And there's some interesting spots where you want things to be provably correct. But for me to go in and say, it's like, okay, well, this is why they do this, because we know that because of the Curry-Howard correspondence, that type checking is the same as proving a theorem. And how now can I have proof carrying code that can guarantee to have certain types of things? It just gets massively complicated. It just gets over the heads of any undergraduate that didn't really try to pursue this as a specialty. And just not ended up with just basically an MS in this, basically not just taking a bunch of graduate programs on this topic anyway. So for the vast majority of programmers, it just makes no sense. And not only that, but there's newer ideas in type checking that add wrinkles to the equation. One being is that you can do some interesting things around contract-based types and how do you express those. Like TypeScript does a lot of this stuff that's very interesting, where they have the any type, which kind of allows it to say, oh, well, you have a function that can return anything, but also maybe not return anything. And you can put some interesting contracts on, and that gets really complicated because TypeScript itself, because they add these types of things and they add in this idea of like, well, given this in the code, infer what this type should be returns. It basically ends up making it so that the TypeScript type checker itself can be used to run an actual program. It's Turing complete in the sense that you can use the types to create a set of primitive assembly operations that you could then say, and someone actually did do this, compile Doom into. So yeah, somebody actually did run Doom in the type checker. It takes a lot of time to render that first little page in the console, days literally, but you can get there. And the thing about it is that adds a bunch of wrinkles, but it adds ideas into how you could do things like in terms of type checking and verification that are not that are now outside the static pure functional programming view of types. For those who are interested, you can look at more on what are called dependent types. That's kind of where that work is being done. And so to summarize, I could get a little bit more into monads and get a little more theory of it. Like, okay, this is what it ends up being. But from a practical standpoint, writing them is incredibly more difficult than using them. Using them, honestly, the best way to kind of do this is that understand now that they're doing this voodoo because they just want to do things in this purely functional way, and that you are just being a benefit of being able to ignore most of that, so you can do things like do this, do that inside that do thing. That's pretty the way to do it. And where it comes down to is arguably it's not needed and practical and large, and which is why Haskell has a very, very limited domain of usage, and less so F sharp, but F sharp also kind of suffers from the same type of thing, which is basically why would you do this in F sharp, even though F sharp has some interoperability, is a little bit less opinionated in certain types of things. It's not necessarily relaxed enough that it makes sense over just using another language like C sharp, which is unfortunate because there are 2 or 3 things that F sharp does so spectacularly well that it's something that should be used quite a bit more often. Haskell, because it's so opinionated, kind of puts itself out of the reach of being useful, but in all but the most very specific domains. But it's still going to be an area of active research. That being said, I'll say that a lot of the research of what's being done in languages has now moved on from Haskell and is now focused on a language called AGGA, which is kind of inspired by Haskell syntax, but really is a much more oriented around theme proving and proof checking, and is even less practical than Haskell is in terms of being useful for a large set of domains. If you want to get really, really interested in, basically types is theorem proving, and like I said, the Curry-Howard correspondence Curry-Howard correspondence as they call it, then AGGA is a great tool to pop up, and it's cool because it's not like it's actually fairly nicely bundled together. It's fairly easy to install, and it does have a Visual Studio Code add-in as well as a Vim and Emacs support. So it's not one of those things where you're like just going off and being stuck in the just having zeros tool support and trying to hope it works, it doesn't crash half the time you run it. So it's very interesting in that regard. But again, what I would say, and this is kind of why I'm biased on this, if you really are interested in learning more about functional programming and why things like an immutable state can be useful, and want to learn a little bit more about higher order functional programs, in terms of writing functions that take in functions and can potentially return functions, I think Racket is just a better way of doing it. Racket is also not very practical in the real world, but there are still enough real world libraries there. And not only that, but Racket doesn't pretend to be like, oh, the amazing solution to all solutions for stuff, versus being specifically designed to help you learn more about how programming languages work. And I think engaging with these concepts from the Racket programming experience would be much more accessible to people than doing it from the Haskell experience. And not only that, but basically I would be reluctant to go off and go to somebody and say, hey, if you really want to dig into this, you can do it by doing Haskell first, but you would be remiss by not engaging with the languages that kind of were the forefathers of functional programming languages, which is basically the Lisp dialects, of which Racket is one. And so I put it out there. And of course, the thing about Racket is that, you want to do monads in Racket, it's easily done. And so you can do experimentations with that as well. And there's other variations on the language where you want to learn other things about how Haskell wants to do certain types of things that you can do in Racket as well. So there's that. So, and again, thanks for watching. Hopefully that sheds a little bit of light onto why monads seem to be endlessly confusing, and why they are best left to basically people that design languages and libraries. And you should basically don't worry if you can't get a deep understanding of how they actually work in terms of even trying to use them in a programming language like Haskell. I hope to see you in the next video. And of course, if you made it this far, please like and subscribe.